In this lesson, we'll be graphing simple rational functions, so we're continuing our look at rational functions. And in this lesson, we'll be combining all of the things that we have learned, and none of these will be super complicated, and none of them will have slant asymptotes, so we don't have to worry about that in this lesson. So the steps in graphing these, when you're not using a calculator, is to factor the numerator and denominator. We always do that first so that we can see what we're working with. The common factors between the numerator and denominator that cancel will give us the holes in the graph. That's step 2. Put it in proper rational form and identify the horizontal. We will actually be using these shortcuts that I've put together. In the last video you saw these, so we'll be applying all of this in the lesson today. Find the roots of the denominator. These determine the vertical asymptotes. Those are the ones that don't cancel. Find the roots of the numerator, and that'll give us roots of the function. In other words, the x-intercept, where it crosses the x-axis. Set x equal to 0 and solve for y. We'll get the y-intercept from that, just like with any function. And then draw smooth curves through the intercepts and approaching the asymptotes. And then anything that's not clear, we'll use what is called sign analysis to determine where the rest of the graph goes. Alright, so let's move to example 1. Alright, now for example 1, it says, in the following examples, sketch the graph of the given function, labeling all intercepts and asymptotes. Note that there will be no slant asymptotes in this lesson. Also give the domain. Okay, so the first step, if you recall when we looked at this list, was to factor the numerator and denominator. So we have 4 over, factor this denominator, that would factor to x minus 2 quantity squared. If you factor it out, x minus 2 times x minus 2. So that part's done. And then we'll start a list of all of the other things that we need. So we'll need the horizontal asymptote. We'll need vertical asymptote, or asymptotes. We'll need holes in the graph. We'll need the x-intercepts or roots. And we'll need the y-intercept. Once we find all of those things, we'll do sign analysis from there to determine any other parts of the graph that we're not sure about. Also, they want the domain, so we'll list that as well. So we'll list all of those things each time. Alright, so horizontal asymptotes, we'll go to our list. Horizontal asymptotes, we're using BOBO BOTN EATSDC. So this one is, and you can go back to previous videos to have a discussion on that from our lesson on horizontal asymptotes. I believe that was lesson 3 in this unit. So this one is bigger on bottom, so that would be this part, bigger on bottom. Our horizontal asymptote is just y equals 0, so that's easy. Horizontal asymptote, y equals 0. Vertical asymptote, looking at our list here, vertical asymptotes occur with factors in the denominator that do not cancel. And again, this list, all my students have it. If you don't have it, take a screenshot of this and it will help you immensely getting through these rational problems. So vertical asymptotes, factors in the denominator that don't cancel. So this x minus 2, we can only have it, even though it's x minus 2 times x minus 2, it happens twice. It still only gives us one vertical asymptote. So we would add 2 to both sides. We get x equals positive 2. So we have a vertical asymptote at x equals 2. Holes in the graph occur, looking at our list here, holes in the graph occur from factors that cancel in the numerator and denominator. Well, we don't have any of those, so none. We have no factors that canceled between numerator and denominator. Alright, now roots of the function, so roots, the x-intercepts, those are factors in the numerator, top, that do not cancel with factors in the denominator. So we don't have any factors in the numerator up here, so we have no x-intercepts, none, no roots. Y-intercept, the y-intercept occurs when x is 0, so we can evaluate our function when x is 0, so f of 0 would be 4 over 0 minus 2 quantity squared. So that would be 4 over 4, which is equal to 1. So our y-intercept is 0, 1. And the domain is x cannot equal anything where we have a vertical asymptote or hole, so that would just be x cannot equal 2. That's it for that domain. So we have all the information we need to make a rough sketch. If there is anything that is unclear, we will do what is called sign analysis to figure that out. So what we do know is that we have a vertical asymptote at x equals 2, so it's a good idea to put that in first. So x equals 2 here is our vertical asymptote. We have a y-intercept at 0, 1, and we know we have a horizontal asymptote at y equals 0. So based on this information, we can say confidently that we have our graph is in this section. It's going through that y-intercept and approaching the vertical asymptote this way. That is because it needs to approach this horizontal asymptote as x approaches negative infinity, way over here. And it needs to approach this vertical asymptote in this section as well. And because the y-intercept is here, that tells us it must be in this section. It either had to be here or here, but based on the y-intercept being right there, it tells us it's got to be up here. That's the only place it could be. So then we need to determine, okay, is the rest of my graph here or is it here? Based on the asymptotes, it has to be in one of those two places because I know I have to approach this horizontal asymptote as x approaches infinity, and I know that I need to approach this vertical asymptote in some way. So I can evaluate the function, say, right here at an x value of 3, and if the graph is down here, then I'll put it there. If that y value is somewhere in this section, I'll put it in that section. So we'll evaluate. I'll do it up here. F of 3 would be equal to 4 over 3 minus 2 quantity squared. So that would be 3 minus 2 is 1, 1 squared is 1, so 4 over 1 is just 4. So that tells us that we have the point 3, 4 up here somewhere. So that means the rest of the graph has to be up here like this. So that's what that one would look like. We could put it in the calculator and verify it, but that would be the rough sketch of that graph. All right, let's move on to example 2 next. All right, for example 2. So the first thing that we need to do is factor this completely. So the denominator actually will not factor. X squared plus 1 will not factor. It's not going to cross the x-axis. If we think about just x squared plus 1 on its own, that would be a parabola that's moved up 1. So it has no roots, therefore it will not factor. So x squared plus 1 will not factor. But the numerator part will. So that would leave us with this if we fully factor it. We want to multiply to negative 12 and add to negative 1. So those two numbers would be x minus 4 and x plus 3. And that would all be over x squared plus 1. So it's fully factored. So because there are no factors in the denominator, that means we can already say that for wholes there are none, because no factors cancel between the numerator and denominator, and there will be actually no vertical asymptotes here because we have no factors in the denominator at all that would not cancel. So no factors in the denominator. Remember our list. Vertical asymptotes and wholes come from factors in the denominator. Factors that cancel are wholes, factors that don't cancel are vertical asymptotes. So that part is answered. Now for horizontal asymptotes. Well, looking back at the original function here, when it was multiplied out, we had a square term on top, square term on bottom. So that would be the exponents are the same. Looking at our BOBO BOTN EATSDC, that's the acronym that we're using. If the exponents are the same, we divide their coefficients. So looking back at this original function, I'll write it right here real quick. X squared minus x minus 12 over x squared plus 1. Exponents were the same. We had a largest exponent of 2 in the numerator, largest exponent of 2 in the denominator. So exponents are the same. Divide their coefficients. There are implied 1s in front of these. So 1 divided by 1 is 1. So the horizontal asymptote is at y equals that number. So y equals 1. All right, now for the roots. The roots occur when we set the factors in the numerator that don't cancel equal to 0 and solve. So we have roots at x equals 4 and at x equals negative 3. Okay, this x minus 4 factor gives you a root of 4. Remember, you just set it equal to 0 and solve. Add 4 to both sides. Get x equals 4. Okay, that's that part. And then set x plus 3 equal to 0. Solve, subtract 3. Shortcut is they have opposite signs compared from the factors to the roots. So there are our roots. Get rid of those. Okay, so now that leaves us with finding the y-intercept. The y-intercept occurs always when x is 0, so we evaluate f of 0. So that would be filling in a 0 for x everywhere, 0 minus 4 over 0 plus 3, or 0 minus 4, 0 plus 3 in the numerator, and then 0 squared plus 1 in the denominator. So that would be negative 4 times 3 up top and 1 on bottom. So that would be negative 12 over 1, which is negative 12. So the y-intercept is 0, comma, negative 12. Okay, the domain is x cannot equal anything that causes vertical asymptotes or holes. So that we don't have vertical asymptotes or holes, so that would be in all real numbers for the domain here. Okay, now we should have enough information to sketch. We'll do sign analysis if we need to, if we can't sketch the graph based on what we know. So we'll put in a coordinate plane here and put in the information we do know. So we know that we have a horizontal asymptote here at y equals 1. So we'll put that in. So that is, we need to approach that for our end behavior as x goes to positive and negative infinity. We know we have roots at 4 and negative 3. Put those in. We know we have a y-intercept down here at negative 12. So based on this information, we have no vertical asymptotes or holes. We only have a horizontal asymptote. So we know that it has to be, based on this information, we have to go through the roots and the y-intercept and approach this horizontal asymptote at the far left and far right. It must be shaped like this. So it's going to drop through that root right there, through that y-intercept, come up, go through that root, and approach that horizontal asymptote at the far right and far left. So based on the information that we have, it must be shaped like this. It could be verified with the calculator, but the shape has to be just like we see here. So we'll end part 1 here, and I'll work 2 additional examples in part 2.